On today's episode of On.NET, we're going to be talking about how to use .NET tools with Kubernetes to diagnose ASP.NET Core thread exhaustion issues. Check it out. Hey, welcome to another episode of the On.NET show. Today we're going to be talking about ASP.NET Core thread exhaustion issues with Mike. Hey, welcome to the show, Mike. Thanks for being on again.
Yeah, absolutely. Thanks for having me, Rich.
So how about you tell us first, first introduce yourself and then tell us what thread pool exhaustion issues even are.
Absolutely. So my name's Mike Rousos. I'm an engineer on the .NET customer engagement team. We're a customer-facing piece of the product team who help to make sure that customers are able to get started successfully with new .NET and Azure app development offerings. So today I thought I'd talk about thread pool exhaustion because it's a common performance problem we see in .NET Core apps. And so I thought, hey, let's just take 10 minutes, walk through the easy ways you can diagnose these sorts of problems using the .NET CLI tools in Visual Studio.
Right. And so do you need, there's obviously like multi-threading. Do you need to be using that in order to run into thread pool exhaustion or not?
So the way we typically run into it is when you have an ASP.NET Core app that's synchronously blocking. Because ASP.NET Core will be multi-threaded for you automatically. Every time a new request comes in, a thread pool thread will pick that up and serve the request. But the problem is if you have some code which maybe you didn't make as asynchronous as you could, or maybe old code that you moved over and haven't updated to be async, you end up with these synchronous calls, and the thread that's serving that request is now blocked until that call finishes. Whereas if in an async model, that thread could go off and serve a different request while we wait for the async operation to finish. And what ends up happening is all of the threads in the thread pool get blocked waiting for whatever this external dependency is that you're calling synchronously. And then when more requests come in, they have to wait for a thread to become available, and it slows things down. Eventually, users start getting timeouts, stuff like that.
Right. So maybe a simple example would be we have these synchronous file APIs. Like if on every request, if you're opening up a 200 megabyte JSON file with the synchronous APIs, yep, and then blocking on that being loaded before you process it, I assume that would kind of lead to this sort of problem.
Yeah, that's the sort of thing that we see. In fact, I've got a demo we're going to look at where I'm making a call to a database, and I even tossed in like a task dot delay just to make sure it was nice and slow. But any sort of external data access typically is where you hit this.
Yep. Okay. Well, how about we just jump right to that?
All right. Perfect. Let's go ahead and get my screen shared, and we will take a look. So one of the reasons that this issue in particular is interesting, I think, is because sometimes you don't realize you have this issue when you're just testing locally on a dev machine or in a staging environment without a lot of load. It comes up when you do more perf or reliability testing, or when you go to production and you have a lot more users. And at that point, you're usually running someplace other than an environment like what you developed on. A lot of customers nowadays are running on Linux or in Docker containers and Kubernetes, and it makes it a little bit trickier to diagnose. So I wanted to show off some of the tools we have for collecting diagnostics in those scenarios. So so that we can do that, I've set up an AKS cluster, and I have a demo app. It's very simple running there. So if I do a kube control.get deployments, you'll see that we've got a deployment called scenario 1. Give it a minute. There it goes. And within that, we have a single pod, which is hosting our app. So let's suppose that we already know that this app is working well when I test it on my dev box, but when we get a lot of users sort of concurrently hitting it, things start to slow down as more users come online. And we want to figure out what's going on. One of the easy ways you can sort of get a high-level overview of what's happening in your app is to use the dotnet-counters tool, which is a cross-platform command line tool that shows event counter information, similar to like perf counter information, on .NET processes. So I'm actually going to exec into the Kubernetes container here, and we're going to run that tool so that we can get an idea of what might be causing our app to slow down in this case. We're going to exec into that pod.
Now, this means that we would have had to have deployed that tool to that into that container when we built it.
Good question. So that used to be how you did it, because we installed the tool using the .NET SDK about, I don't know, 6-9 months ago. Improvements were made to the .NET CLI tools so that they can just be downloaded directly from the internet now. So I didn't install it here.
Okay,
that's how
perfect.
I used to do it. But nowadays, you don't have to worry about that, because that was always a hassle. People would get into their production environments. They didn't have the SDK, and it was always a pain. So in this case, I'm able to I'll just make a new folder to keep things neat, but I can go into the tools folder. I can just use curl to curl it down, essentially, or wget or whatever you want to just download the file from the internet. So we'll go .NET-counters, Linux, x64. We'll call it .NET-counters here. And that's all you need to do to install the tool. So it's a lot easier than it used to be. We'll go ahead and mark it as executable so that we can run it. And then it's got a couple different commands. Sometimes you'll start with a .NET-counters PS to see the managed processes that are running that you could monitor. And in this case, we've just got process 1 because we're just running in a Docker container. So we'll go ahead and just do a .NET-counters monitor on process 1, and that's going to show us these event counters. Now, I'm just using the default set, which is going to be the runtime event counters. So we get things like CPU usage, some garbage collector information, the different generation heap sizes and frequencies. We get thread pool information, which is going to be interesting for this investigation, information on lock contention, JITted methods, all sorts of stuff. It's a really useful tool for getting a high-level overview of the health of your app. There are also other sets of counters you can use to get information that would be ASP.NET Core specific. So you can opt into ASP.NET Core counters to see informations on like response times, stuff like that. And you can even enable your own custom event counters. If you've instrumented your app using event counters, then you can enable those with .NET counters as well, so you can watch those metrics in real time as well. So we're watching this right now. Everything's sort of in a steady state. Nothing's happening, really. No CPU usage, no real memory usage. So let's go ahead and apply a load. I'm going to use Siege, which is a command line tool, to just simulate 100 concurrent users for 1 minute hitting this product category endpoint. And the product category endpoint just goes out and gets information on product categories from a sample AdventureWorks database. So if we come back to .NET counters and look, you can see we still have no CPU usage. Allocation rate is low and steady. There's no GCs happening. The only thing that's interesting here is we see this thread pool thread count is sort of monotonically increasing at a very steady rate. And that's a red flag. The fact that we have a lot of stuff in the thread pool queue kind of makes sense because we've got 100 concurrent users all sending requests. But we shouldn't be increasing the thread pool count like this. In an ideal ASP.NET Core application, everything runs asynchronously, so a very small number of threads can serve a large number of requests. That's not what we're seeing here. We're seeing that as time goes on, the runtime is expanding the thread pool as quickly as possible to handle these incoming requests. So likely what this tells us is that there are thread pool threads being blocked on some sort of long-running task. And maybe it's something that has to be long-running that we're going to have to work around, or maybe we're just not doing async right. But thread pool threads are getting blocked, and we're needing to add additional ones. You can see in the end, our transaction rate was quite low, which is problematic. This is a simple app that should have hundreds or thousands of requests per second. So now that we've identified that the thread pool is needing to add a lot of threads, how can we take that next step and understand why that's happening? For that, it's actually a very easy problem to solve. There are other performance problems that are harder. This one, you've got a lot of thread pool threads, and they're all stopped waiting for something. So all you need to do is collect a dump that's going to let you look at those call stacks and see what they're waiting on. So for that, we have another CLI tool, which is super useful because it's a cross-platform tool, just like .NET counters, that you can use right from the command line when you're SSH'd into a container or anywhere. And that's going to be our .NET dump tool. So if I do a, let's see, do I have it? Let's see, I'm looking for .NET dump. There we go. So it's same as .NET counters. I'm going to curl down .NET dump. locally, although.
Right, and that's from some Microsoft-owned endpoint. Like this
It
isn't
is.
random software on the internet.
No, it is not. It is not random software on the internet. I forget where this particular aka.ms redirects to,
Yeah,
but it is a Microsoft-owned one, which I know is important for a lot of customers because in their production environments, they're not able to hit just any internet site. But this does resolve to a fairly official Microsoft one, which I'd have to go look up.
actually, do you know you can use -v
Let's try it.
on curl?
Is it lowercase v?
Yeah, just beside the L. Yeah.
Haven't tried that. Let's take a look. Okay. Download.visualstudio.microsoft.com, it looks like. So, it ends in a Microsoft.com. So,
We're good to go. Yeah.
You're good to go. Awesome. So let's go ahead and use that. So once again, I'm going to apply some load. And so if you're not familiar with dotnet-dump, it's an easy to use command line tool which allows you to collect, manage dumps, and also analyze them. So in this case, I'm going to bring it back to Windows because Visual Studio makes this really easy. But if you needed to analyze the dump right there in your production environment, you could use the dotnet-dump analyze command to open it up in the command line and use SOS commands to explore the dump that way as well. So there's a lot of options. But what we're going to do is we're going to do dotnet-dump collect. We're going to collect a dump for process 1. There are different types of dumps you can collect, but the default full dump is fine in this case. And so that just writes it to disk. Okay, this is still running, so that's good. And so now at this point, we've got a dump here. And it's fairly large, it's 800 megs, so I'm not going to copy it to my dev machine live because that'd probably kill our online session here. But instead, I've got a dump that I copied earlier from this exact same scenario. So we're going to go ahead and take a look at that one.
And what was the mechanism by which you did that copy?
Good question. So because it's in Kubernetes, I can do kube control CP to copy files out of the containers. If it was just a Docker environment, it could be a Docker CP. If this was some other Linux environment, you'd copy it with whatever mechanisms made sense for that environment.
Right. So you used the standard Docker mechanism for this.
Exactly.
Okay.
Exactly. Yep. Nothing special about that. And I was going to show that you can analyze with dotnet-dump. I forgot while I was exec into my container, but that's, there's really nothing to see there. You do a dotnet-dump analyze, and then you can run SOS commands like CLR threads to list the managed threads or CLR stack to see the stacks. But a better way to do it is to do it in Visual Studio. So you can see here we've got a dump. It's a little bit smaller. I must have gathered it slightly earlier, but it's the same exact scenario. The one thing I'm going to do first is I want to make sure we have all the symbols and debugging files we need to get the best possible experience. If I were to open up like this, Visual Studio would show me stacks. It would give me some information, but I can get more information by making sure that I have all of the necessary files present. So the first one I'm going to want is I am actually going to do a kube control copy because I want to make sure that we have symbols for my app so that we can associate locations in code with source lines so that I can go and see where exactly in my source the problem may have been coming from. So I know that I deployed my app to the app folder, and let's see, it was target app.pdb. We're going to copy target app.pdb locally. And then the other thing that I'm going to do is I'm going to use the .NET Symbols tool, which is yet another CLI tool that allows us to go out to Microsoft Symbol servers and download debugging files like DAC and DBI files for arbitrary dumps. And this is very useful because we can use this. We can say -debugging to say that we want debugging files like that DAC and DBI, and we can say host only to say that we want the .NET host. And then we just specify the dump that we want these for, and this is okay, probably I've got the wrong file name. So let's try again. Host only, that one. Well,
no, I think it's .NET Symbols.
Yes, it is. I have an S that I don't need. Thank you, Rich. There we go. All right. So now we're downloading these. If you were to have built your own .NET framework and runtime, you would just have to get these yourself. But as long as you're using one that Microsoft built, these are all available. So we've got the stuff all locally now. So now we can open this dump any way we want. We can use .NET Dump. We can use WinDBG. On Linux, it would be LLDB. But really, the best experience nowadays is Visual Studio. It used to be that Visual Studio would only open the Windows dumps, but now, just continue without code, we have the ability to open Linux dumps on Visual Studio as well and get that nice debugging experience that people are used to. So let's go ahead. I'm just going to drag and drop this thing so I know where it came from. We've got our dump here.
Wow.
Open it up with VS.
That looks pretty straightforward.
It's very straightforward. This is an easy scenario. It's just a matter of knowing that these tools have these capabilities. So you got here the modules that are loaded, information on the dump file. So we're going to go ahead and debug managed. And as soon as it starts debugging managed code, it's going to jump right in, and we can see we've got call stack information. Here's a list of threads, and you can see we've got a few dozen threads. So I could very easily just start navigating between these different threads and looking at the call stacks, and from that I could probably figure out where the problem is that's causing the threads to all be blocked. But there's an even easier way to look at this. If we go to the debug menu and go into Windows, go to Parallel Stacks, the Parallel Stacks view in Visual Studio is a really nice visualization of the overall state of threads in the app that you're debugging in this dump. It gives a nice sort of macro view of what's happening, and then from there you can drill down into things that are interesting. So in this case, you can see even though we had dozens of threads, there's really only a few things shown here. We've got a couple of main threads, a few things that were spawned out of thread helper.threadstart, and then you can see it groups together threads with similar call stacks. So we have 36 threads that all share this call stack, and then they split off into one of these two very similar set of calls. And so if we zoom in a little bit here so it's obvious, you can see we have some highlighted stack frames, which are the ones we have symbols for. So we've got some stuff in the .NET framework itself, but right here at the top of the stack, we have category repository.getAllCategories, which I know is one of the APIs from my app. I recognize that here. And so this is likely where the problem is. As I hover over it, you can see the different threads which make up this collection of 36. So I can click on any one of these. Probably we can click on a couple and just make sure they're all doing the same thing, but the call stack's exactly the same. So any of these are going to be similar. So I can select that. And now, move this out of the way, we will have moved over so that we're looking at that particular thread, and we can see the call stack. We can see, if I go to locals, I can see any locals information here, like what's going on in this repository object. Here's my SQL connection. The thing that's particularly interesting, though, is that we can see where we are in this file. So this is just a simple repository pattern that's using Dapper to go out to a database and get some information. And you can see we're doing this db.query, but it is a synchronous query. And just to make sure that things are slow, because hitting Azure SQL databases is super fast if the query is not complex, I tossed in a task.delay as well. And I put a .wait on it, which is always a bad sign if you've got .wait and .result littered around. But between these two calls, we can see this is where this thread is sitting at the time when I took the dump. And so now we've identified the place where there was something that was sort of slow running, either the delay or the database access, and it's being done synchronously. So this thread can't handle any other work until these complete. And so now that's why the thread pool is having to go out and add more threads. We can go back, we can navigate to other threads. We're going to find they're all sitting in the same place. And so now we know what we have to do to fix it. We go in here, we make sure that, this method becomes asynchronous. We do an await here. We get rid of the .wait, and we call query async instead of query. And we're going to see our throughput go way up and not suffer from the same thread pool exhaustion issue. So it's that easy to figure out where you're blocking your threads if you run into this.
So just so that everyone understands, so we're doing dump debugging here.
Yes.
And I think of that as, it's a very similar experience to interactive debugging. It's got all the same windows, and obviously you're looking at your source code, except for the interactive part. Like, right, there's no stepping. This is like a process that
won't do anything.
That's locked at a single point in time and can't go backwards or forwards.
That's right. It's locked here. We can't step to the next instruction, but it allows us to inspect the state of the app at the time we captured that dump.
Yep.
Yep. All right.
Okay. So are you going to show us or tell us what happened next?
I guess I can. I wasn't sure how we're doing on time. I actually thought ahead and I made a get all categories async, which does the await task.delay and await query async. And so if we want, we can stop debugging this and we can go ahead and we can run my siege command again. But this time, let's add /async at the end.
Yeah,
because what that's going to do is, well, I don't have it open here, but I've got another endpoint that's going to use this async API in my repository instead of using the synchronous one. And it's going to be very different. In fact, if I can be fast enough and let's see, exec back into that container, we can start up .NET-counters again. And you'll notice that there's never more than 3 to 5 thread pool threads. So go over.
Yeah, that's what I was wanting to see, to kind of put a bow on this.
Let's see. So monitor. So we've still got stuff, still got load being applied. But now when it starts up, so we've still got stuff in the queue because new requests are continually coming in, but the count of thread pool threads is 1. Also, our CPU usage is 99% because there's nothing else blocking this now. So the app's running as fast as it possibly can. And now the bottleneck is just, well, how fast can Kestrel serve requests? And it's working overtime because the thread pool has basically nothing to do because those 2 or 3 threads there were able to handle all of the hundreds of incoming requests because they'd see, oh, we need to get something out of the database, kick off an async task, now go handle the next request while we wait for the async thing to come back. So if we come over here, we've got 2,600 requests per second instead of whatever it was before. So it's obviously an enormous difference. And this is a contrived example because the app is doing nothing but that database access and the task.delay, which you would never have in a real app. But it does show the difference of what it looks like in .NET-counters and the fact that it makes a big difference at the end of the day when you've got a lot of concurrent users hitting that endpoint.
Right. So just before we finish up, some people might see like, oh, you hit 100% CPU. Wow, that .NET must be inefficient. But it's actually the exact opposite, right?
Yes.
Which is we're trying, like, that's the goal, which is make the CPU get to 100% because it means there's nothing blocking there.
Yes.
It's like, that's what we always want to see.
Exactly. Yeah. I mean, at some point, there's going to be a limit to how fast we can serve requests. Something's going to be the bottleneck. And previously, it was our thread pool. Now it's the CPU, which is kind of where you want to get to because then you say, well, if we need more, well, we add more hardware. We scale up, we scale out. Now, there are instances where I've seen customers have inefficient code on hot code paths, and maybe we can do a future session where I can show you how to debug that because it's actually just as easy. You can use .NET Trace instead of .NET Dump, and you can open up those traces on your dev machine and look at where those hot code paths are. If we were to do that right now, we'd see that most of that CPU time is just being spent by the ASP.NET Core host, which is what you want. If we had an inefficient app, we'd open it up and we'd find out, oh, it's actually being spent by some other piece of code that maybe could be made better. So then when you've got that CPU at 99%, you either you get more hardware or you find a way to make your code more efficient. And so maybe in the future we can take a look at that.
Awesome. Okay. Well, I think we'll put a couple links in the description so that people can see the link, figure out where all those tools are.
Yeah.
But yeah, thanks again for being on the show.
Absolutely. Thanks for having me, Rich.
Yeah, I think people will love this kind of topic because it's very, very, very practical.
Yep, it's very.
Yeah, okay. Well, this has been another episode of the On.NET Show talking about ASP.NET Core and how to diagnose thread pool exhaustion issues. Thanks for watching.